All right. Abnormal molecular masses, experimentally observed molecular masses on the basis of colligative property, which is different from the molecular masses calculated from its chemical formula. That we call it as abnormal molecular masses. We have studied colligative properties, four colligative properties, and this colligative properties depends upon the number of solute particles. This depends upon number of solute particles. Directly proportional to the number of solute particles. It does not depend upon the chemical nature, right? And now, when we have the relation with molecular masses of solute, that is inversely proportional to colligative properties, means inversely proportional to number of solute particles. If the solute particles is lesser, number of solute particles, not chemical nature, then colligative property will be lesser, then molecular masses will be high. All right, this is a concept from where you will go through all the Van factor, calculation of association, dissociation. This is important. The molecular masses of solute is inversely proportional to the colligative property, means inversely proportional to the number of solute particles. All right. Now we have three cases of the solute particles. Whether the solute particles is unchanged, whether it is associated, or whether it is dissociated when we add in the solvent in order to become solution. So what will happen to the solute particles when we are adding in the solvent, whether it is dissociating this solute particle, non-dissociating, or associating? The three cases are there. The first case is what we have. Molecular state remains unchanged. Molecular state of solute remains unchanged. Molecular state of solute, which remains unchanged. Example, we can take non-electrolyte. We have urea, cane sugar, glucose. So what they are saying, molecular state of solute remains unchanged, non-electrolyte. Example, we can have urea as an example, we have glucose, sucrose. All right. When the solute remains unchanged in their molecular state, what does it mean? It means it is neither associating nor dissociating in the solution, which means the number of solute particles which is present in the solution, that will remain the same because it is neither associating nor dissociating. If the number of solute particles is there, colligative properties will be remain there. So molecular masses of the solute will not vary, will not change. It means what you will not get abnormal molecular masses. Means the masses which you have calculated on the basis of colligative property and you will calculate from its chemical formula. Say example urea. Urea is having from its chemical formula 60. And when you calculate it from the colligative property, also you will get molecular masses of that solute urea 60. Because the number of solid particles, that is the molecular state of solute particle, remains unchanged. Neither it will associate nor it will dissociate. All right. So solute do not undergo any association or dissociation in solution. First important point, case one. Solute do not undergo association or dissociation. When they do not undergo association and dissociation, the number of moles of solute present in solution is same as added before dissolution. So whatever the number of solute you have taken, you put it in the solvent, become solution. Before adding into the solvent that number of solute particles and after adding, that is dissolution, that will remain the same. So number of moles of solute present, number of moles of solute, the number of solutes present in solution is same as added after dissolution. Since the number of moles of solute present in solution is same as added after dissolution. Is it clear? So when the number of moles of solute present before and after adding the dissolution is same, so we will get exact molecular masses. We don't get any abnormal molecular masses. So this is the cause for not getting abnormal molecular masses. Three conditions are there. When the molecular state of the solute remains unchanged in the solution, it means it neither associates nor dissociates. And the number of solute particles will remain the same before and after dissolution. Since the number of particles, solute particles are same, so the colligative property has its normal value. Colligative property will show you the normal value and we don't get any abnormal molecular masses. All right. So the what will be the molecular masses effect? Molecular masses obtained from on the basis of colligative property that will be equal to means same as obtained from its chemical formula. When they both are same, because I have told you abnormal molecular masses obtained from colligative property and from its chemical formula, it will be different. So what is the cause for different abnormal molecular masses is this only. Number of solute particles. When this remains the same, the molecular masses from colligative and from its chemical formula will remain the same. Colligative property has the same value as its normal value. All right. So there will be no abnormal molecular masses in case number one when the molecular state of solute remains unchanged for non-electrolyte, example urea, glucose, sucrose. All right. Now we will move on to case number 2 and case number 3. And whenever you have to write all these are the key points which I have put it here. Molecular state of solute undergoes association. For example, benzoic acid. Now, association means here two or more molecules, all right, combine together, aggregate together to give a bigger molecule, to give a larger molecule. That is association. Small particle, small entity, small molecules combine together to give you a bigger unit. That is association. Two or more molecules combine together, aggregate together from association. All right. World Health Organization. Small, and all the countries united together. United Nations. So what is happening here in the benzoic acid? If we take the benzoic acid, we have C6H5COOH. When two molecules combine together, and associated, they are known as dimer, as in case of benzoic acid. If three molecules give you a trimer, four molecules combine together associated. If here is three, trimer, four, tetramer. All right. So association is going on. So now in association, what will happen as in this case, I'm talking about taking the example of benzoic acid, which is a dimer here, which undergoes association. Number of solute particles is reduced to 1/2. So in case of association, the number of solute particles is decreasing. When the number of solute particle is decreasing, so what will be the effect on the colligative property? Colligative property will decrease. When the colligative property will decrease, we have molecular masses of solute that will increase. All right, got it clear? Abnormal molecular masses in case of association will increase. Reason? When they go and form association, number of solute particles, when we are talking about the dimer, so dimer may it is reduced to 1 by 2, half. Formation of dimer, this is dimer, reduces the number of solute particles to 1 by 2. How this is happening, when we will calculate the association, there also I will explain why here we talked about 2 here. If we take a general example, we will discuss any. A will give you N. Here half is reason is this, because here N we have taken 2 and here we got it 2 is here. As in case of benzoic acid I'm talking about. The number of solute particles is reduced to half. This can be 1 by third. When the number of solute particles is reduced, what will happen? Molecular association leads to decrease in the number of solute particles. When the solute particles decreases, so abnormal molecular masses will become high because colligative property will decrease. When it will decrease, the molecular masses will increase. So we will get abnormal molecular masses. And that abnormal molecular masses is high as we calculated from its formula. All right. This is about case number 2. Now, the third one we have case number 3. Molecular state of solute undergoes dissociation. Say electrolytes. Electrolyte example KCl, NaCl, CaCl2. The molecular state of the solute undergoes dissociation, and dissociation results in increase in number of solute particles. And KCl, K plus 1 mole, Cl minus 1 mole, 2. The number of solute particles as in case of this, the number of solute particles as in case of KCl increases the number of solute particles to twice. After dissociation, increases the number of solute particles to twice after dissociation as in case of KCl. When the solute particle increases, colligative property will increase, and when the colligative property increases, it means their molecular masses will decrease. they have lesser abnormal molecular masses as calculated from the qualitative property as compared from its chemical formula. Because the solute particles after dissociation becomes twice. All right. And Van Hoff factor, it is what? Observation value of qualitative property to the calculated value of qualitative property. That is a ratio between the observed upon calculated. All right. Now, since we have already seen that, that is, this is directly proportional to the number of solute particles. I have already told you just now only. All right. So they depend upon the number of solute particles. And molecular masses is inversely proportional to the number of solute particles as they are inversely proportional to the qualitative properties. So now we can also write it here. I can also be just reverse of this. So this is a molecular masses of, if it is a molecular masses of observation, so this will be the qualitative property because inversely. So I can also be written as calculated molecular masses of solute upon observed molecular masses of solute. They have defined it as this also and this also. All right. That is a calculated upon observed molecular masses of solute. Now, I depends on the molecular state of the solution. I depends on the molecular state of the solution. This I depends upon the molecular state and from here we can say that I can be is equal to 1 when molecular state of the solute remains unchanged. And I will be less than 1 and I will be greater than 1. In terms of when I is greater than 1, it means dissociation of solute particles takes place. And if I is less than 1, it means association will take place. So I value depends upon the molecular state of the solute. I is equal to 1. It shows that molecules neither associate nor dissociate. All right. Greater than 1, dissociation will take place, and lesser than 1, association will take place. And after introducing I by Van Hoff factor, all the colligative formula which we have done, that will also change with respect to this I. If we were using the relative lowering of vapor pressure, P naught P upon P naught is equal to mole fraction of solute. So we will introduce I here. So this will become I into mole fraction of solute. Delta TB, KB into M. We will introduce I here. Similarly for delta TF, I, KF into molality. Pi, I, N, R, T. The modification of the colligative properties when the Van Hoff factor is introduced. So this will become the modification of colligative property with respect to these colligative properties. All right. Now we will go through firstly the calculation of degree of association. Calculation for the degree of association that we have to be. Now the calculation of degree of association के लिए first what you have to go through, we have a formula. I is equal to total number of molecules, total numbers of molecules associated total number of molecules associated of upon actual number of molecules taken. Yeah, total number of molecules associated, yeah, after association upon total number of molecules taken. You have to apply this formula. All right. I is the total number of molecules after association, yeah, associated upon total number of molecules taken. So total number of molecules taken means uh, that is actual number of molecules taken. Now, what we have to do it here, say an example, I have told you any, this will give you a n. All right. Now, actual number of molecules taken, so suppose I have taken one. One is what? Actual number of molecules taken, that is one. And out of actual number of particles, all the particle will not form association. So those particles, those entity in that molecule is forming association. That will be alpha. All right. So 1 minus alpha, this is undergoing association. Alpha here goes for association. And 1 is the actual number of molecules we have taken. So what will be here? What we will get it here? Alpha by n. Is it clear or not? Why we are getting alpha by n? Say example I'm giving. Take a compound X. Make it to X2. You have taken 1000 entities in X, which is the actual number of molecules, out of which, say, 400 goes for association. So here what will come? 400. But this entity, this is divided by 2, you will get 200. That's why we have divided by n here. Because this 200 will give you what? X out of the 400 which goes for association. Got it clear here? Alright? Clear? So 1 minus alpha will become alpha by n after dissociation. To put this in the I formula, so what I we have, so what will be the total number of molecules associated? 1 minus alpha plus alpha upon n. So this will become 1 minus alpha plus alpha by n upon actual number of molecules we have taken 1. Got it? So y is equal to 1 minus alpha plus alpha by n. Is it clear? Now, this can also be written as 1 taking out alpha as a common, one minus 1 upon n. So I becomes 1 minus alpha 1 minus 1 by n. Got it clear? Now, we got it here. I is equal to 1 minus alpha 1 minus 1 by n. So I, this one will give come here if we talk about, but alpha is in the minus, so we will take it this here. Alpha will be is equal to 1 minus I upon 1 minus 1 by n. This is the formula for calculation of association. Got it clear? 1 minus I means 1 is here, this will come here, so minus I, and this will go here, so alpha 1 minus 1 upon n. All right. Now, I we know that m calculated upon m observation. So we put this I in this formula. Alpha is equal to 1 minus I upon 1 minus 1 by n. Instead of I, what we put it is this one. The formula will become, after putting this alpha is equal to 1 minus m calculated upon m observed 1 minus 1 by n. So alpha will become m observed minus m calculated upon m observed. LCM we have taken upon 1 minus 1 by n. So this you have to calculate it. All right. If you want, you can solve it. This also, this will become n minus 1. N upon n minus 1. This can also be written as n minus 1 upon n. So either you can solve it here or you can write this also as this taking the LCM. So this will become n minus 1 upon n. So this is related with I, observed and calculated molecular masses, which you have to do it.